Hi there, Mr. Sutton with the Pre-Cal Honors 3-7 lesson on graphing rational functions. In this one, we will indeed be graphing these rational functions now that we know how to find all of their different features. And as a real-life application, we'll analyze a function to see what's going on with the race completion time in a river race. We're going to start off with a little application here. Percy enters a 100-mile canyon river race. Let's let x be Percy's speed in still water. We want a function f of x for the time it's going to take Percy to finish the race, if he's rowing with a 20-mile-per-hour current. So take a sec, see how far you can get with writing this function. All right, let's see what you came up with. Now, in general, the time is going to be the distance divided by the speed. And the distance, I mean, it is what it is. It's 100 miles. The speed is the 20-mile current plus however fast Percy is rowing. So for distance, we can write 100. For Percy's speed, well, they told us in the problem, let x be Percy's speed, and then we're adding another 20 miles per hour to that. So 100 over x plus 2, that's going to be our function. Woo, there we go. So let's go ahead now and find all the intercepts, asymptotes, and holes, if any, for this function. Take a sec to do that. For the x-intercept, if you're setting this thing equal to 0 and solving, you can't really make the top of this fraction become 0, so there is no x-intercept. For the y-intercept, we're plugging 0 in for x, so that's 100 over 20, which is going to give us 5. So in real-life terms, that means if Percy's speed is 0, if he just lets the river carry him, he's going to finish the race in 5 hours. For vertical asymptotes, this function is already as reduced and canceled as it can be, so whatever makes this denominator 0 is going to be a vertical asymptote, and that's going to be, if we set that equal to 0, negative 20. So what that means in real life is if Percy rows backwards at 20 miles an hour, matching the current, he's never going to finish the race. For holes, since we didn't have to cancel anything out, there's no holes here. For the horizontal asymptote, this is a bottom-heavy function. We have x to the first power down here and just a constant upstairs. So this is going to be y equals 0. And in terms of what that means in real life, as x gets larger and larger and larger, I mean, let's say Percy could somehow row 1,000,000 miles an hour, he's never going to be able to do better than 0 for a finishing time. Now that we've collected all that information about the river race function here, here's our information we just collected. We're going to go ahead and use this information to graph this function to see what it looks like. So this sounds a little bit intimidating, but it's actually not too bad if you have all the information you need. We're going to start with the easy stuff, with putting points on the graph. So your x-intercepts, your y-intercepts, put those on the graph, and then the asymptotes. So we have no x-intercept, we have a y-intercept of 5, and to make this easier, I'm making the grid lines on my graph go by tens just so we can fit everything. So we have the y-intercept 5 right here. We have a vertical asymptote at negative 20, the x value negative 20, so right here. And we have a horizontal asymptote at y equals 0, so that's the x-axis here. Now the key to graphing these, we know that these rational functions always hug the asymptotes. They always follow the asymptotes, approach them, but we need to figure out which side of which asymptotes our function is on. So the key here is that you need at least one point on each side of all your vertical asymptotes. There's just one vertical asymptote, so we need to figure out the point over on this side of it. We already have a point on the right side of this vertical asymptote. We need a point on the left side as well. The good news is, if you didn't get that point already with your intercepts, you can still plug in other x values into the function to get another point. You could have done this already. So I'm going to pick an x value over on the left side here, like negative 30. And for my additional point, I'm just going to plug this into my function. So we have 100 over negative 10. That's going to give us negative 10 for the y value. So we have the point negative 30, comma, negative 10. Now that you've got a point on each side of the vertical asymptote, you're going to go through those points and approach the asymptotes. So you have to do those two things at the same time. So here we're going to start on the bottom of this horizontal asymptote on the left so that we can go through this point without crossing any asymptotes. So we go through that point, and we approach that vertical asymptote. And then to go through this point, we're going to have to start up here. We're going to approach that asymptote, go down, and then approach the horizontal asymptote as we move to the right. For the next two problems, we're actually going to give you all the key features of the rational function. So here's a list of the intercepts and asymptotes. You could get them yourself, but we're just trying to save a little bit of time. And we're going to let you focus on the graphing, given these statistics here. So pause the video, and using these parameters, see if you can graph this out. All right, let's see how that went for you. So x-intercepts, there's none. We don't have to do any of that. Y-intercepts, we have one at -3. So that is right down here because we're going by 2's with these grid lines. We have a vertical asymptote at x equals 1. So vertical dashed line going through 1 right there for the x values. And we have a, we don't have a hole, but we do have a slant asymptote, not a horizontal, but a slant asymptote at y equals x plus 1. So y-intercept of 1, slope is 1, so we're going up 1 over 1, up 1 over 1 like that. That gives us a slant asymptote. And we're almost ready to draw the branches following the asymptotes, only you'll notice that we're missing a dot somewhere on the right of this vertical asymptote. We know that we're going through this dot on the left side, but on the right side we don't really have any point to anchor us. So we're going to get an additional point by plugging in an x value that's to the right of this vertical asymptote. And I'm not sure which one to use. I'm just going to use 2. It's the first one I can think of to the right, and it's an easy number to plug in. So I'm going to plug 2 into the original function and see what y value we get when we plug in 2. So in the numerator, we've got 2 squared, which is 4, plus 3 is 7. Downstairs, 2 minus 1 is 1. So this is a grand total of 7. And it looks like I'll be able to fit that on the graph. If not, then I would move a little further out with my x values and probably get less extreme y values, up to a point anyway. So we've got a point at 2, 7, which is right here. And now since I've got a point on every side of the asymptote, the vertical asymptote, I'm good to go ahead and draw my branches. So we draw one branch in here that's approaching but not touching the slant and the vertical asymptote, like so. And then we do another branch going through this point and approaching the asymptotes in the, I guess, the upper right there. And that's it for that one. There's no holes to place on there, so we're good. So for this next problem, we have this function here where they gave us all these statistics, and they actually simplified this function for us as well, which was nice of them to do. So pause the video and see if you can graph this one based off of what they gave us. All right, so going through the intercepts first, we've got an x-intercept of 0, and that also doubles as the y-intercept. So having both of those doesn't really help us because they're both kind of the same. Next, we have a vertical asymptote at x equals 2, so that's right here. And we have a hole at -1, but we don't really have a graph to put the hole on, so we're going to hold off on that, no pun intended. We do have a horizontal asymptote at y equals -3/2. So that is, let's see, here's 1 1/2 horizontal asymptote going through there. Now, next thing I need to do here, I noticed that I have a point on the left side of my vertical asymptote, but there's no point over here on the right side. So I'm going to get an additional point by plugging in an x value that's over here. I'm going to go with the x value 3. I can always try other ones if it doesn't work out for me. And when I do this, I'm going to use the simplified version of the function here. I could use either one, but why make my life harder if I don't have to? So we'll plug 3 into this simplified version. So that's going to be, let's see here, we've got -3 times 3 is 9. Down here we've got 6 minus 4, which is 2, so 9 over 2, negative. So we have a point then at 3, -9/2, which is -4.5, which is right about there. So I have a branch going through this point on the left side, approaching my asymptotes but not touching them. I've got another branch going through this point here, again approaching but not touching the asymptotes. And now the holes, like this x equals -1, you've really got two options there. One option is to draw the hole last. So I can see at the x value -1 right here. This is where my graph is. So the hole is going to go right on the graph at that x value right there. Now, another way to do this is you could actually plug in the x value for the hole into the simplified function after you cancel, and that would give you the y value of the hole. So if we do this, just for the sake of argument, we've got, let's see here, 3 times -1 would be -3. Down here we'd have -2 minus 4 would be -6. So we have -3 over -6. 3 negatives gives me a negative, and that reduces to 1/2. So the y value would be -1/2 based off of our algebra. And if you look here on the graph, this y value does appear to be about 1/2. So that's just a good way to check your answer, even if you wait until the very end to put the hole on there. As a little quick wrap-up question, take a minute to answer this one. When do we need to find additional points? And how do we know which x values to plug in? A lot of students are kind of confused about this, so let's see what you come up with. So we need to find additional points whenever we're missing a point on one side of a vertical asymptote. We always need to have a point on each side of the vertical asymptotes. And the x values we're going to plug in are just going to be easy x values on the side that's actually missing the point. So don't make your life any tougher than it has to. Pick something easy. So that's it for this lesson. Until next time, this is Mr. Sutton signing off.